Let's begin with a simple example where you actually do not see any pointers. We have here function main, and it's the only function in this program that we at least defined by ourselves. When the function gets called, a local variable a gets allocated, then we assign 1 to this variable a, then the value of a gets printed, and then we actually already reached the exit point and we are done. Now what you know from previous videos is that local variables are allocated on the stack, which is in this example at least, or for what I want to show you in this video, not that relevant. However, what is relevant is that variables are located in memory. And you should think of this variable a, once it was allocated, as a box in the memory. So we have here some part of the memory, some memory cells. And from these memory cells, this block, this box, for example, might be used for variable a. Then we say this is the memory location used for variable a. And you actually know from previous videos that the number of memory cells, the number of bytes used for this memory location, this information can be accessed from the compiler by using the size of operator. So you can get with size of a the number of bytes used for variable a. Now, every memory cell has an address, the index of this memory cell. The memory is organized in an array, and every array element has an index, and this index is called the address. Now here in this picture, let's say this address might have the value 1024, which is a nice number because it's 2 exponent 10. Then this 1024 would be the address of variable a. Now of course the address 1024 was made up by myself. In general, you also can access from the compiler the information about the address of a variable with some operator. So the actual address you can access with the address operator, which will be just an ampersand followed by the name of the variable. So ampersand a might be, for example, like here, 1024. Now instead of making up numbers, let's simply change the program so that it's printing these numbers, that it's printing the address of a and the size of a. And this is what you see here. In the second printf, I'm printing the address of a, and in the third printf, the size of a. You also see that I'm using here different placeholders. For printing the address, I'm using the placeholder %p. P is short for pointer, and this will print some hexadecimal representation for the address. And what you see from my program, the value that is printed out is certainly not 1024. And actually on your machine, you might get a different address. For size of, I'm using the placeholder setu. Set, I guess, is short for size and u is short for unsigned. And here you most likely will see the same. You will see here that 4 bytes are used for this variable a of type int, which is true for many architectures, by the way, but not for all. For example, on an Arduino, you would see that 2 bytes actually are used for an integer. So the size of a type is platform dependent. Also, just out of curiosity, you might want to try to use here something like %d, a different placeholder. Then for the address, you would probably get some value that doesn't make sense. For example, in my case, I see some negative value. And for an address, this doesn't make sense because an address is always an unsigned value. So it can be 0 or positive. So I guess now it's time to actually talk about pointers. In short, a pointer is a variable in which you can store the address of another variable. And this is what happens in this program. You see that we now have 2 variables. We again have variable a of type int. Let's mark it green. And we have another variable ptr for pointer, which has this strange type arrow to an integer. But in the beginning, just think of two variables as two boxes in the memory. So let's draw some piece of memory with two boxes. So we have a green box for variable a, let's say here. So this is a, not initialized, and because it's a local variable, its value is undefined until we assign a value to it. Then we have a second variable, ptr, and here I use this purple box, so this is ptr, also not initialized, not a good coding style, but yeah, let's start with that. Now, in the beginning, nothing changes compared to before. We first assign a value to a. That means after this statement was executed, a has the value 1. Then we print this value, and then we again see a has the value 1. Now, interesting is then this here. We assign the address of a to variable pointer. Now that means if this is the address, %a, for example, 1024, again, just made up, but just to have concrete numbers, then we simply store this number, this address, in variable pointer. So it's now, after this statement, stored here. And the reason why we call ptr a pointer, and in this case, after this assignment, a pointer to a, is that we can think of the meaning of this number stored in ptr as pointing to variable a. And that's almost it. Now, the next interesting thing is actually the next assignment, where on the left-hand side, we have this asterisk followed by the pointer variable. And this asterisk in front of a pointer variable means that you're referring to the variable at the end of a pointer. That means this asterisk ptr refers to this box. And into this box, we then write the value 42. That means this 1 gets overwritten with 42. And then you see, when you now again print the value of a, you no longer see 1, but actually what is stored in this green box, the value 42. Before I tell you a bit more about how the compiler is dealing actually with pointer variables, let's consider some application for pointers first. Recall that in ABC, like in C, when you pass an argument to a function, the function receives a copy of this argument. And this is what I show you here once again in this example. We have in function main this variable a. Let's mark it green. And when we look at this variable in memory, it means we can think of a green box, a memory location used for variable a, which in this case is initialized with 123. Then, of course, when you print out this value, you will see 123. Then we call function foo, and we pass a as argument. And that means this parameter n in function foo gets a copy of this argument. That means when we are now in function foo, we have another variable, which I denote with this blue box. This variable is called n, and n has a copy of this argument. So n will have, when we enter the function, the value 123. Then we change n, we assign 42 to it, then it means that we are changing the value in this blue box. We change it to 42. And then we return to function main. That means we continue with this printf statement here. And here we are printing our variable, the variable a from function main. That means we print the value in this green box, which is still 123. Now also make sure that you understand that it's obviously irrelevant how you call in function foo the parameter. Even if you would call it a here and here, it simply would mean that this memory location is now used for a variable a, but it's a different variable from the variable a in function main. This function foo still has its own variable, and this variable gets initialized with a copy of what you pass as argument. So with this, it's impossible that function foo changes the value that you pass to it in its original location. You cannot change this memory location by a call of function foo. However, if you use pointers, like in this example, it actually is possible. It is possible that this variable a gets changed by a call of function foo. Let's see how this works in this example. We again have this variable a as before in function main. So again, let's use a green box for this memory location. So we have here a initialized with 123. Then we print out the value of a. And here we have the first difference. We are not passing a to function foo, but the address of a. So let's say the address of a, ampersand a, let's assume it's again 1024. Then we pass a copy of this value to function foo, and function foo receives this copy in variable n, which is now a pointer to an integer. So that means in function foo we again have a memory location for this parameter. This memory location is used for variable n, but compared to before, this memory location is used for storing the address of a variable of type int. And in this memory location, we have 1024 when we enter the function. And here in this statement, in this assignment, we are not changing the value of n. We do not assign a new value to n or change the value stored in this blue box. What we are changing is what is at the end of this pointer. So actually I should use here a notation which is more consistent. N is pointing to variable a. That means asterisk n refers to this memory location. And into this memory location we are now writing 42. So let's erase 123 and we now assign 42 to this memory location. And then we return. And after we return, we again print the value of a. That means the value of this memory location. And this time we see 42. That means with this construct, it's possible that function foo is actually changing variable a. Now what's the application for that? Replace this function call with a call to function scanf, where scanf receives two arguments. The first is a format string with placeholder %d, the same that we use for printf for printing an integer, and the second is the address of a. This function scanf is declared in standard I/O. Now when you compile and run this program, you should see the following. The first printf prints out the value 123. Then you have to type in an integer and also hit return. Then scanf returns and the second printf will print out the integer that you typed in. And in the exercises, you have to implement your own simple scanf. So basically, you have to replace the implementation of foo here. Instead of assigning a fixed value 42 to what is at the end of pointer n, you basically have to read in here character by character by using getchar, check whether this character belongs to a digit, and with that assemble the value, the integer value that the user wants to type in, and then store this value at the end of pointer n. Now, I was often using this phrase, writing a value to the end of a pointer. Let's review the previous example and reflect what this phrase means. So this is the example where we have a variable a and a pointer variable, ptr. Variable a will be again represented with this green box with this memory location for variable a. So this is for a, and a purple memory location for ptr. Then we first assign 1 to variable a. So after that we have here a 1. Then we assign the address of a to ptr, which means that the address of a is stored in ptr. That means we can think of it as if ptr points to a. And then here we are not changing ptr, we are changing what is at the end of this purple arrow. That means we change something here. We change the value 1 into 42. Now in ABC I introduced a notation which I hope is good for teaching purposes. Instead of writing asterisk ptr, you also can write this, ptr followed by a pointer. And the meaning of that is that, or the purpose of that is that you actually see that you are writing something to the end of this pointer. And this is completely equivalent to what you saw before. That means ptr followed by a pointer. This expression is equivalent to asterisk ptr. It's just maybe more intuitive for beginners.